Hi all of you, my name is Vinay Wagh and here I am with a quant session, the series of session that we are going on for CAT 2025, the revision series. So in this series of revision, today I have number systems as the first chapter from the quant section. Number system because the weightage is high, the range is around 20 to 50%. There were years where number system was around 40 to 50% in the entire quant. Not just the weightage part, number system also acts as a foundation for quite a few other chapters for you to master. These days we have seen even in geometry, permutation, combination, ratio, proportion, HCF, LCM, averages, factors related theories are getting built up and they are prime requisites for those. So I have chosen number systems to start with. So there are around 5 questions. 4 out of these 5 questions are from CAT 2023. One of the question is from some other CAT. Right. So this will act as a revision of one of the family of questions of the entire number system. So to start with, here's the first question for us. It's asking what is the sum of the first two natural numbers each having 15 factors. And there's a condition given 1 and the number itself that is to be included. So what you need to know first is for any given number, if you break the number in factors, let's say prime number 1, prime number 2 and prime number 3, there can be more than this. So the total number of factors can be found out as x plus 1 into y plus 1 into z plus 1, and if there are more than this, then it will go on. That's how we find the total number of factors. So this is the theory or the initial part of the knowledge that one needs to have. Question is, what is the sum of the first two natural numbers? Maybe there are many natural numbers. Question wants us to stick to the first two natural numbers and add them up, each having 15 factors. Total number of factors are 15. So how can I have 15 as the total number of factors? 15 can be 1 into 15 as 15. 15 can be 3 into 5 as 15. These are the two cases. How else can I have 15? For 1 into 15, having it in this format, I can have some prime number raised to 14, right? So prime numbers raised to 14 and 14 plus 1, 15 will be the total number of factors. It's a big number, but let's first delineate the cases and then we'll worry about the first two natural factors. 3 into 5, so it can be of the format a prime number raised to 2 and another prime number raised to 4. So 2 plus 1 will be 3, 4 plus 1 will be 5 and 3 into 5 will make it 15. Cool. So first exploring the case number 1, if it is 2 raised to 14, it's a big number. I don't think I will try and work out how much it is. Not very difficult, but let's see if we really need it. This part is, let's say, 2 raised to 2 into 3 raised to 4, one of the case. 2 plus 1, 3, 4 plus 1, 5, 3 into 5 is 15. Noted. The other possibility is just swap the bases, right? Third, 2 and 3, first two prime numbers we have taken, is 5 going to be a part of it if I take less as the exponential and 2 as the other part? It's again 3 into 5, 15. So how much is this? 2 square is 4, 3 raised to 4 is 81, that's 324. This is 3 raised to 4, that is 81. This should be 3 raised to 2. So 3 raised to 2 will be 9 and 2 raised to 4 will be 16. So 16 into 9 will be 144. I had written 2 raised to 2 into 3 raised to 4. Then I swapped it 3 raised to 2 into 2 raised to 4. So that was small correction. 5 square is 25. 2 raised to 4 is 16. 320 and 80 is 400. So this does not get included simply because we want the first two natural numbers. So 324 plus 144 is 468 and that's our answer. So 468 is the sum of the first two natural numbers that act as the factors that generate total number of factors 15, including 1 and the number itself. The number of positive integers less than 50 having exactly two distinct factors other than 1 and itself. So again, a question of same family where you have string of prime numbers, and for you to find out total number of factors, you add 1 to the index, each index, and then get the total number of factors. You want the total number of positive integers. Condition is it should be less than 50, and they should be distinct factors. You should not take 1 and you should not include the number itself, right? For example, 8. 8 is 2 raised to 3, so there are 4 factors, 3 plus 1, right? And what are the 8 factors? 1, 2, what are the 4 factors? 1, 2, 4 and 8. So these are 4 factors of 8. We should not take the number itself and 1, so the other factors are 2. Just an example. This way we have to find out all possible numbers that can be roped in. So what's the idea? We want the total factors as 4. So it can be simply a prime number raised to 3. 3 plus 1 will make it 4. So I can have 2 raised to 3 in this because 2 raised to 3 is 8 and 8 is less than 50, the condition. I can have 3 raised to 3 in this. 3 cube is 27, 27 is less than 50. I cannot have 5 raised to 3 because 5 raised to 3 is 125, that is not less than 50. So two such numbers, 8 and 27. These are the numbers that have 4 factors, and if you exclude 1 in the number itself, there are 2 factors. Otherwise, we can have p and the other prime number, and they should be raised to 1. 1 plus 1 will be 2, 1 plus 1 will be 2, and 2 into 2 will make it 4. How many of this type? It can be 2 raised to 3, it can be 2 raised to 5, it can be 2 raised to 7. I'm just taking the prime numbers in order. 2, 3, 5, 7, now 11, and after 11 what do we have? 13. And I'm also noting 13 into 2, 26, it's less than 50. 17 into 2 is 34, it's less than 50. 19 into 2 is 38, that's okay. 23 into 2 is 46, that's okay. Next prime number is 29. 29 into 2 is not less than 50. 2, 3, 4, 5, 6, 7, 8. So 8 such numbers are done. Now bring in 3. 3 into 5. 3 into 2 is already done there. So I'm starting with the prime number more than 3. 3 into 7. 3 into 11. 3 into 13. 3 into 17. But 3 into 17 is 51. That's spoiling the given condition. 3 into 13 is 39, that's okay. 1, 2, 3, 4. So these are 4 more. And now I'm taking 5. 5 into the prime number more than 5 because 5 into 3 is taken care of. 5 into 2 is covered. 5 into 7, 35, that's okay. 5 into 11 is 55, that's not okay. So this is 1. So altogether 8 plus 4 plus 1. So 13 such numbers. And we have 2 more over there. So 13 and 2, we have total 15 such numbers. So the answer to this is 15. Nice. Next question. How many factors of this huge number are perfect squares that are greater than 1? 1 is also a perfect square, but the question doesn't want 1 in it. It's a big number. Thankfully, it is already broken in prime numbers except that 10. So it is left for us to break it in prime numbers. And after that, we have to, assemble the prime numbers that have even exponentials. So any prime number raised to even exponential will make it as a perfect square. So let me just write this number 2 raised to 4 into 3 raised to 5. 10 can be written as 2 into 5. So that's 2 raised to 4 and 5 raised to 4. So this can be rewritten as 2 raised to 4 and 4, that's 8, 3 raised to 5 and 5 raised to 4. Okay. So how many factors that are perfect squares? So for perfect square, from the collection of 2's that we have, we can have 2 raised to 0, 2 raised to 2, 2 raised to 4, 2 raised to 6 and 2 raised to 8. All these are perfect square. 1, 4, 16, 64, 256. They all are perfect squares. The family of 3. 3 raised to 2, I told you the exponential should be an even number. 3 raised to 4, 3 raised to 6 is not available because the maximum exponential that we have is 5. So 1, 2, 3, 1, 2, 3, 4, 5 from this side, 1, 2, 3, 3 from 3's, and from 5, 5 raised to 0, 5 raised to 2, that's 25, 5 raised to 4, that's 625, and 3 more. So 5 3s are 15, 15 3s are 45. But we are not allowed to have 1 in it. So I remove 1 and we are left with 44 such numbers. And that's how the answer is 44. Right? Let n be the least positive integer such that 168 is a factor of this big number 1134 raised to n. If m is the least positive integer such that 1134, the same number brought in here, is a factor of 168 raised to m, then the possible combinations that we can have of m and n, what is the sum of it with the condition that n is minimum. Nice. So let's first factorize this and then we can get some ideas. 168 can be written as 2 into 84. 84 is 42, uska half 21. So this is 2 raised to 3 and 21 is 3 into 7. Right. I broke 168 as prime factors. Then 1134. This can be written as 2 into 2 5s are 2 6 are 2 7s are. Further I can write it as 2 into 7 into 81, and 81 is 3 raised to 4. Nice. So 168 can be broken as this, and the prime factors of 1134 can be written in this form. Nice. It was 1134 raised to n. Alright, so I have raised to n in my work. So the question is least possible value of this value n. 168, this becomes a factor of this. So for this trio to be a factor of this, all the exponentials here should be respectively smaller than the same base here. So 2 raised to 3 and this is 2 raised to 1. How can 8 be a factor of 2? So for that n has to be 3. 3 into 1 will act as 3. So 2 raised to 3 can be a factor of 2 raised to 3. This will be 7 raised to 3. So 7 raised to 1 is by all means a factor of 7 raised to 3, and same way 3 is taken care of. So the minimum value of n that we can have is 3. Noted? Now move on to the second part. M is the least positive integer such that 1134 raised to n. Same number, I'm just rewriting it. 2 raised to 1 into 7 raised to 1 into 3 raised to 4. This is raised to n, and I know n. This becomes a factor of 168 raised to m, and 168 is 2 raised to 3 into 3 raised to 1 into 7 raised to 1 raised to m. Now this is a factor of this number, which means the exponential of every prime number should be smaller than the respective exponential of the other prime number. So here I have 3 raised to 4 further raised to 3, that's 3 raised to 12. I'm just spotting the biggest possible exponential. And here I have 3 raised to 1 into m, this is m. So 3 raised to 12 has to be a subset of 3 raised to m, and for that m has to be 12. So the minimum possible value of m is 12. So with m as 12, n as 3, our answer will be 12 plus 3 as 15. So the possible value of m plus n with n being minimum, least positive value, it is 15 as the answer, right? What's the difference between possible perfect square factors and perfect cube factors of this number? If you are noticing, most of the question, almost all of the questions are dealing with the similar base and the foundation that one requires. Even here I have to factorize and take care of things that will make it perfect square and perfect cube. So first thing first, let me again factorize this 129600. Let me break this as 1296. So 100 is what? 2 into 25 into 4 is 100. 1296 can be written as 2 into 648 का half 324, 150 and 12, 162, 81. So this is already 2 raised to 4 and 81 is 3 raised to 4. And I am writing this as 2 raised to 4 and 2 is 6, 3 raised to 4 and 5 raised to 2. Done. So the number is now broken in prime factors, simplified. Now perfect squares. Yeah, you can have 2 raised to 0, 2 raised to 2, 2 raised to 4 and 2 raised to 6. 2 raised to 6 is 64. That's a perfect square. So 4 of them. 3 raised to 0, 3 raised to 2, 3 raised to 4, 81 is a perfect square. So only 4 of them, only 3 of them. And in the case of 5, it's 5 raised to 0, 5 raised to 2, only 2 of them. 4 into 3 into 2 gives me 24. Why am I multiplying them? See, I already have an array of perfect squares. 2, 4, 16, 64. And these are also perfect square, but a perfect square getting multiplied to a perfect square is a perfect square. For example, 16 into 9 is 144. We know 144 is a perfect square. Or 64 into 81 will act as a perfect square. So that's why we multiply them. So this is set of perfect squares. Then the second part was perfect cubes, again from this. So perfect cubes can be 2 raised to 0, 1 is a perfect cube. 2 raised to 3, 8 is a perfect cube. 2 raised to 6, 64 is 4 cube. 3 of them. From here it is 3 raised to 0 and 3 raised to 3, only 2 of them. And from this case, it's 5 raised to 0. There's no space for 5 raised to 3, so it's only 1. So 3 into 2 into 1, that is 6. So 6 perfect cubes and 24 perfect squares. And the question wants the difference of this, and the answer is 18. Right? So this is yet another question of prime factors, squares, cubes, and things related to it. So these were the 5 previous year CAT questions, CAT 2023, and I'll come up with another video next time with more questions on number system, because only 5 questions will not suffice. My objective in this PPT was to cover a family of questions, right? Next time I'll bring another family of number system questions that will take care of the revisions, the theory, and then the application part of it. So do let me know if there are any suggestions from your side, what should be the family of questions in the next PPT, and I'll surely agree to that part. So till then, see you, bye.